Never underestimate escape.
But yeah, but you read budget inheritance.
Joris, do we want to open a window or something?
Yeah, perfect. Yeah, okay, so next one is Patrick Titiano from Libre to talk about still stories in the kernel. You're ready. Maybe you guys need some short break before I start. Fine.
Yeah. Fresh air.
Yeah, fresh.
It's okay.
I'd say that will
I have no.
Okay, so let's start. So hello everybody, my name is Patrick Titiano. I'm working for Libre, an embedded systems engineering firm. I'm so-called system power management expert. I've been in the Linux business for quite a lot of time, more than 10 years. And I am very pleased to be here with you at this first Power Management Summit. I've been invited and
can you please raise the volume because...
Yes, okay. So it's just, I'm very pleased and honored to have been invited to this first summit. Thanks a lot. Yeah, so what brings me here in front of you is discussing about the need of power management instrumentation in the Linux kernel. And I will be presenting different purposes and reasons why we should invest more time into instrumentation and tooling. So first, the menu of the day. So a quick introduction about the discussion we will have. And then trying to give some answers to a few questions, high-level questions like why do we need power instrumentation, what's needed, what's available, and what's missing. And then trying to do more of the next steps. It's going to be open for questions. Why do we need power instrumentation? What's needed? What's available? Yeah, that's a few seconds delay. Okay. Okay, so I think one of the major issues the Linux community is facing today regarding power management is the lack of power data and power instrumentation. Usually the dev boards we are all using doesn't have any probe points, so we cannot measure the power consumption. Then if we still want to do some measurement, the equipment for that is pretty expensive, and it's usually not affordable for hobbyists or enthusiasts that are doing things at home. And we know it's a big part of the contributions. And also on the power data, usually the silicon vendors, they don't share much data about the power consumption of their silicon. We may just get some lifetime durations and not more. So we don't expect this situation to change in the future, unfortunately, because the belief is that it's only interesting for a handful of people, and so it's not worth investing in. And this is obviously not true. Like it's a key and central problem because we have so many connected devices that runs on a battery that power management is at least as important as performance. All this is forcing us to actually have our own custom scripts, custom hardware modes, We do everything by hand, and each time there is a new platform to study, we need to redo it again and again. So this might look like a dark picture, but actually there is still a hope for better situation, and this may come through power instrumentation. Because by correctly instrumenting the Linux kernel, we may be able to have all this missing information. We just got a very nice presentation previously that shows it a little bit already. Oops. So the first question I'd like to cover is why power instrumentation? So I'll go through different, I would say, main purposes of instrumentation. I think one of the holy grail we have is to enable dynamic power measurement, well, actually it would be estimation of a platform without the need of any external measurement circuitry. That would enable any single person to do power management study from students to companies. And there would be no extra cost for expensive development boards. The second purpose is being able to dynamically detect power leaks by closely tracking runtime usage of peripherals. We would know exactly which peripherals are active, which ones are idle or disabled. We would detect necessary running clocks, necessary running devices. We would be able to track CPU freaks, CPU idle states, etc., etc. The purpose of power instrumentation is to also capture system power trace and be able to post-process it. So this slide is just what has been demonstrated before this presentation. That would enable a better, more efficient power debugging, and that also enables power regression tracking. And that's super important. Usually today, we commit every day tons of patches, maybe tons, but lots of patches, and usually there is no single idea of what is the power impact of those patches. Some may completely break the power, some may improve it, and we don't even know it. So being able to do CI on power is very important. Something maybe it's not a first thought is that power instrumenting the kernel would enable a better power modeling. We would be very efficient in predicting what could be the power consumption of a next generation. If we have a trace of the Linux of the power consumption of a given kernel on a given silicon, by just updating the silicon data, we expect the software to run the same, and so we would have power consumption of the next gen silicon almost for free. And yeah, we could even compare platform to platform, but I'm not sure silicon vendors would like it. Last purpose I wanted to present is being able to develop closed-loop power management policies. Before AAS, typically all the CPU freak governors, CPU idle governors were working in an open-loop way, meaning that they collect some data, take some decision, apply it, and then do it again on the next period, but actually they don't really consider the effect of what they have decided, so it's open loop decision. Now, by collecting power events and re-ejecting this to the policies, then it's going to be way more efficient because the policy can really react correctly, like, oh, okay, this decision was wrong, I'm not taking it again. Or this was right, okay, I'm taking it again. And typically that's the open door to very sophisticated policies like self-learning policies, IA, deep learning, whatever. I mean, someday we could just run the policy and it would learn the platform by itself, and we don't need any more fine-tuning. Okay, so to be able to have all these purposes real, what do we need? First, the most important, we need probe points. Being able to save all the various power events that's happening on the platform. So regulator, clocks, power domain, CPU freak, CPU idle, device, GPIO, power transmission, anything that has an impact on the power consumption of the platform, and obviously with timestamps.
That is assuming you actually have access to that information.
Yes. Yes.
Because
so
a number of platforms don't give you nothing.
Yes. Correct. Correct. Okay. The next thing we need is some power consumption data. It's super cool to have all these probe power events, but what we need also is to map this to power consumption. Like if a device is running, how much it consumes. If it's idle, how much it consumes. What's the power consumption of a CPU in a given OPP? All these kind of things, we need to know it. Because then, if we collect this trace and we map it with the power consumption, then we have the real-time power consumption of the platform.
So you want a power model? You want a power model for each device?
No, not really a model, but like how much it is consumed in a given state. It's not really the model. It's not really modeling.
I mean, that's quite similar to what is done in ES.
Yes, it is actually. This was written before I knew ES. But it's exactly that. The dream is coming true. Okay, last thing I wanted to highlight about what's needed is some tooling. Something to plot the power trace we would collect, something to process the trace, and those tools should be generic and cross-platforms. We have some stuff is running. We know Qualcomm is doing a good job for their own platform, and it's partially available to other platforms. Google has the Android trace, but well, it's not Linux generic. Okay, so what's available among all these? So first, in terms of collecting the power events, well, we have FTrace. FTrace is doing all the job for a long time, and actually, it's too bad that a few people knows it. It's super simple to use. It's incredible, and it's so easy to use, and actually, people doesn't know about it. So with FTrace, we can collect all the power events and others, but regarding power management, we have everything we need. We have all the runtime PM events.
So you said the main issue with FTrace is that it gives you an event, but if there is no event, for example, you have this GPIO event, but if a GPIO is never used, you will never know its state. So you need more than FTrace. You need this static where you are starting.
Yeah, we need a start point. That's an issue.
Yeah, that's a common problem.
Yeah. And do you have any way to do that?
No,
not yet. And if anyone in the room has one, please share.
Something kind of similar that we do in this is that, for example, for frequency, if you don't have a frequency governance, which frequency, you never know which frequency you are. So when we enable the CPU frequency event, and we start a workload, we know that this event is traced. What we do from user space, we read the frequency for every CPU, and we inject an event from user space. So a fake CPU freak event. That's okay. That's the state.
That's the same thing for us when you start profiling. You need to know where stuff is in memory. So we start the profile, we start collecting data. It will tell you about new memory maps, but it doesn't tell you about the old ones. So once we start, then we inject all the memory map stuff we find from the profile system for all the tasks we're interested in, which is possibly the entire system. We just inject it into the trace so that we at least have some of the information to start parsing the stuff. But yeah, it's annoying.
Yeah, it's not automatic. I mean, it's something we need to do by hand. So, yeah. Okay. So, everyone in the room is familiar with FTrace? Yeah. So I guess I don't need to. That was a small tutorial, but it's not.
So the proper mount point for debugger is /debug. This is kernel nonsense. That's dragon idiots.
Okay.
That's the past one. The other one is the canonical one.
The proper one is /debug.
Okay.
The other ones they're wrong.
So that's the trace we collect. That's the FTrace. That's an example, and that's what we need to decode and complete. Okay, so what we really miss is the power, what I call a power database or a power model. So we want to know the power consumption of any device in any state, and with that we can rebuild the real-time power consumption. These data are not really published so far, but it's critical for us. Usually we have battery lifetime for selected use case, and that's all. This database would have to be multi-platform, and that's to enable generic tools. A very dumb example, a text file with all the raw data in it, CSV format, but it can be way smarter than that because it's going to be super huge. For once, Android is a little bit in advance. They do have some kind of power database. It's stored in this XML file. Excuse me?
How useful is it?
I think it's not super useful for us because it's not it's too high level. Like it's like LCD screen. It's mainly on peripherals or it's the big picture. It's not going into the details.
It's not fine-grained enough.
No, yeah, it's not. But it's there. It's to show that there is an interest. For me, at least, I use it this way.
There's a gazillion devices and peripherals in computers. I mean,
So typically that's what's used when you open the battery settings panel in your phone, and it shows you how the power is going down, how the battery is discharging, and how much power is used per application or per device, and that's how it is used. So there are different ways to store this database. Could be a single file or structure in user space, but actually it could be also in the kernel or more precisely in device tree.
yeah, but my laptop doesn't have one. I'm just saying.
Yeah.
We have similar things in SPI description. Don't we get similar information?
I comment on that before we get far too deep into this. So there are places in ACPI where people wanted to put numbers like that, and they never showed up. Never. I haven't seen any instance where those numbers, either they showed up, they were just made up. They were not real numbers. So this is completely unrealistic. Nobody is going to do that.
Basically, if Windows does not require it for booting, it's either not there or wrong.
No, so the problem is with getting those numbers in the first place.
Sure.
Yeah.
That's insanely expensive. So nobody is collecting. You know, if you were to profile every single device on an SoC in terms of energy consumption, the power consumption is not the right term, energy consumption.
Yeah, energy.
In terms of energy consumption, you will spend, I don't know how much money on that. And fine, because that it takes time to do that. So nobody does that. We have,
But the guys that built the SOC more or less have an idea, right?
No.
Yeah,
No.
yeah.
Yeah.
At least in mobile phone, we have detail for sure. I was working in a mobile phone manufacturer, and we can provide you the number for any single port domain.
Yeah,
But we don't provide publicly the value.
I used to work
That's
for
the point.
TI, as well. He used to work for ST, I used to work for TI. You have this number. It's just that it's not shared.
Yeah, so maybe.
Because they use it in some complex model already. Because when they design the new platform, everything is modern and they have very fine-grained data. We have it. It's just that it's not shared and they don't want to share it and they don't really know how powerful this data are.
So either it is not doable or it's not shareable.
No, yeah,
because I mean it's like IP, okay, right? It's internal data and they don't want competitors to get it.
So the bottom line is nobody is putting those numbers in there, even if they are theoretically useful for that. So in like in the CPI tables. So that
we need some hope.
We
I mean,
could
it may change.
use some relative values, like there is a table of states, for example, and there is some information on how, on the relationships between them, like which one is, say, draws more power and by how much, right, than the other one, which already is useful because you can then say, oh, if I use this one, then I'm going to know twice as much of the current or whatever in the configuration. But yeah. Again, so there is room for things like that. It hasn't been used for the last 20 years. I have no hope for the next.
I understand. I just like to come back on one of your arguments, being that usually people don't want to spend that much time doing it. I would reply that they are already doing it and way much on a higher grade. Like not doing this in the first place forces everyone on Earth doing it on their own. And once you have your laptop or your phone, whatever, built, you need to learn everything that's happening on your own. If you were okay to share this data in the first place, it's there for everyone. So if you look at just in terms of effort, clearly it's easier to share the data from the start than letting everyone on Earth doing whatever they can, doing some experiments.
Aren't these values available for some devices, for example, Wi-Fi or on the data sheet on the internet?
Yeah, for
Wi-Fi,
peripheral,
Bluetooth,
yes.
or...
I think so. Like I could, for instance, I gave an example of an NAND chip, and actually that I took the data sheet and used it. Okay. So for peripherals, okay. For complex SoCs, not okay.
Okay.
Yeah. Today.
So I think that one of the issues is the representation issue. So if it's an IP, you don't want to give up your raw numbers of power level. You don't want to compare with others on raw numbers. So let's say that we can normalize, and that's something like Rafael would suggest. So you know that it's double if you. But then if you have IPs that are produced by different vendors, and both of them they normalize according to their own scale, do you think this can still be worth to have these numbers? I mean, if you focus on, for example, on pages for HDMI, maybe it can still be useful, yes, no, or if the normalization is not agreed.
So for IPs inside an SoC, it's going to be tightly linked to the technology the silicon vendor is using. So even if it's like a USB, typically the Synopsys USB IP, you can't really publish numbers. Or maybe like ARM is doing on Juno board, maybe we can have this data and use it.
No, I'm talking about normalizing numbers.
Yeah, normally it's a good point. I didn't realize that. Maybe not giving the milliamp or the energy or whatever.
What we do for ES.
Just provide an index.
Yeah.
Eventually.
The energy model we use for energy aware scheduling is just relative. You can use whatever scale you want, but it only works as long as it's the same scale across all your CPUs. And if you're providing normalized data, then it only works as long as it's the same normalized scale you're using across all the subsystems you want to compare. So if you want to, for example, if you want to plan for your thermal budget, it doesn't work if the CPUs are using one scale and your other peripherals are using a different scale, because you can't sort of sum them up and see, am I within my thermal budget or not? So
But there are challenges. I mean, this presentation is like nice slideware, whatever.
yeah,
But we all know those challenges. But it doesn't. It's not done today. It doesn't mean tomorrow it cannot be done. Maybe someday. I mean, the added value of a silicon vendor will be something else, and they don't care anymore about that, so they are more happy to share.
yeah.
Or they realize they cannot survive. I mean, it doesn't. The model doesn't scale.
So it's not like vendors go around and hide their performance numbers, for example. They're happy to produce absolute performance numbers with whatever benchmark that they're using. Power numbers are secret. It's just another parameter describing a system. I don't really get it.
I think it's a habit inherited from the past.
Everything is a secret, except if you can explain why it shouldn't be 3 times over and you're fluid.
I think also it's like usually, well, some of us knows it, but usually silicon vendor goes and try to sell the silicon to people with very nice numbers. But when you get your phone or whatever device built, you measure it and oops, okay, there's a 100% delta between the targets and what I have actually. Can you please explain? Oh, yeah, no, okay. So maybe they don't feel comfortable with that also.
The power models that we have for CPUs don't necessarily come from the vendors at all. No, we derive them with pains. Some pain of
the vendors will not give us that. We have to measure. And it seems like the performance that they publish is marketing, right? It's not technical. It's not even descriptive of user experience. It's just.
But the point was right. Is like if you buy a NAND chip or a memory chip, if you buy a Wi-Fi chip, whatever, you have those numbers. If you look at the data sheet, they must produce it. You buy a power regulator, you have everything you need. The efficiency, you have curves or temperature, you have all the data.
Their customers.
Because you need this data.
Then that what they're selling is Antutu scores.
Yeah, that's right. But maybe it's somehow corrupted by the need of by the mobile industry. Like if it was another industry, I think it was not so high pressure, like so high competitive industry like the mobile. Like every new year, you have to have a new chip ready, and it's putting a lot of pressure on the R&D, and they don't want to go into that mess. Today, again.
Just one comment on yours. It's true that in the energy model we need to normalize across all the CPUs, and maybe also GPU is kind of related.
Yeah.
But the goal there is really to repartition power. So we need this common normalization.
Yeah.
But if the goal here is just to track whatever energy is assumed to consume a specific device, maybe the cross normalization between different IPs is not really required. You can still see that something is consuming double. Because of edge.
Exactly. So it's only if you need to compare power consumption between different subsystems that use different scales that you have a problem.
Yeah.
So if it's only tracking the power consumption in your Wi-Fi subsystem or whatever, it doesn't really matter. But if you want to, for example, control your thermal budget, which is the entire system, then you need something which is on the same scale.
Also, if you're interested in absolute numbers, if you are interested in relative, like apply equation and what's the intensity of my power, then that's no problem.
As long as what you're doing is not trading off power in a subsystem on one scale versus power in a subsystem using a different scale, then you're fine.
Okay, so what I wanted to highlight with this slide is that device tree or ACPI is such a nice place to have this data, because your platform is fully described, peripheral devices per devices. So it's just a single a few attributes to be added, and once you have that, FTrace can export it, and so all the Lisa and other tools based on FTrace have been upgraded for
But I'm wondering if just having the active power is enough, and you don't need also metrics that describe when you are active on a certain state, how much you are using the.
So it's probably some peripherals have different active states, CPUs, whatever, for example. And so yes, maybe. So again, that's dumb examples, easy example, just to make people aware. But you're right, we may need more states. Okay, so I just explained. So yeah, just imagine that AES scheduler would have access to that. Wow. Okay, so that's how is the name of the decode, the FTrace decoder? Traffic. Traffic. So that's traffic. Something to decode. FTrace, we need it, so we have it now. We want to be able to export different kind of statistics. We have had very nice examples. We may want to reformat the FTrace into something that is portable. It has to be multi-platform. You may run it directly on your device under test if it's a PC or more, but you may run it on a host also. That's super useful for automation because we can, on any new commit, we may be able to run it again. That's all for continuous integration. And the idea is that if we are able to get the power consumption of selected use cases on a build server in an automated way, then we can track use case regressions in terms of power. So that's, I think, critical. Because you all know that usually we first enable all the features on our platform, get the performances, and then we say, oops, okay, power is not there. I need to tweak here and then to get the power as best as possible. Well, this example is super easy, and I think there were better examples with Lisa's presentation. Okay, so a static analysis of a trace is giving a lot of information, but it's not enough. Usually, human beings, they prefer to have something more graphical. It's usually very useful to better understand the dynamics of a system. So we need a plotting system, and so we need a plotting application. And that plotting application should highlight us all the various power data, and I'm going to provide an example. So that's just an example. I have a trace I collected with FTrace, for instance, that gives me all this data. So you have the datagrams there, and the power consumption we built. And it's going to be, I would say that we have something, we have today.
And how far have you compared that with the real power measurement? So an idea of how far?
No, I'm not yet there. So let's say we have managed to rebuild, or we have measured the power consumption, the dynamic one. It would be super cool to actually, when you point to a given data, you put your cursor on a given data point, you actually have everything that changed highlighted. So you know why the hell we had this peak there. So while that's okay, I have started Pokemon Go, and it has started the GPU, for instance.
Just to be clear, this is a rendering of what you would like to see.
Yes.
Okay. It's not done yet.
It's a slideware. It's a dreamware. But actually, I mean, given all the Python library we have today, I think it's, I mean, if you measure this, if it's a measured power trace, I think we can have this pretty easily. It's just a way to represent data.
Yeah, I will just, I mean, adding FTrace 7, enabling FTrace 7, it's a cost, and if it's more. Enabling all the FTrace events, can this just drain more power than you want to say?
So you can just
that's the deal you have to make at some point. If you instrument, you know there's a cost.
Yeah. I mean, yeah, my point is just that I'm not sure that we can enable all this
no, not all.
trace full time.
Yeah. we can only enable selected ones. Maybe, okay, I want to check that I don't have, I may check, for instance, that I don't have useless peripheral active, so I would only select runtime PM events, check that, maybe link to some other events because you still need to understand what's happening on your platform. And take things one by one. That could be a strategy when you want to have the minimum impact.
But still, if you are interested on relative changes between different plants, if all the FTrace they had a base energy consumption is always the same, it should be just.
Yeah, but at some point, the overhead generated by trace are so high that it just hide what you are trying to track. That's the
real power consumption.
Yeah, it would be actually interesting to see if that's actually true. I mean, do like experiments where you actually trying to see enabling everything or not enabling actually can be to see how far.
For example, enabling all the scheduler FTrace event can just double your runtime.
Yes.
But if you, I mean, so that's because it's software instrumentation. I mean, if we, on the dev world, if we had access to the debugger, right? I mean, you remember that on some mobile SoCs we had a system check? No, not
you can have TPIU. No, my point is just that maybe some core site, we are coming back to how to access that. It's just that sometimes you can have some hardware IP embedded in the sub that can help you to.
Yeah, but that's for very high perf SoCs, and we may not have access to it. Otherwise, yes, there are hardware IPs that are able to, with zero cost, to export all this data. It's existing for many years. It's just that we don't have access to it, or it's disabled.
So since we are talking about those topics, just want to know that it's a bit of topic, but in a research project we are doing with a few partners, we developed a board with Science Ultra Speed Plus. Right? It has 11 rails of power, and the company making it, we asked it to put probes on it. So we have the I2C converter, so the kernel can read through I2C the consumption. And we also put out the shoot register on the top. So, and using the ETM in the ultrascale, we can get both the trace and the power consumption. So using tool like Lauterbach, you can do the correlation.
Yes.
So if you're going to develop this kind of tool and you would like to test it on the real measurements and so on, then those could be a possibility. Of course, it costs a lot of money, but we are in connection with Union and so on. So all the work which has been done in on power consumption group, which is explained by Luca Deni, exactly will be related also to that. So there could be some possibility for matching the dreamware that you are saying there with actual data from one board.
Yeah. So we've seen that solution, and it's very interesting. There's one big, in my opinion, because that was one of my first ideas, having internal ADC to measure the power consumption. The thing is that then you still need the CPU and I2C to read the data.
Yeah, what I said maybe was not clear. There are also probes on external. You don't need to use the CPU to get the data. So you can go the correlate. You can get this kind of drawing from Lauterbach, where you have the trace of the instruction trace from the ATM plus the power consumption in the same window. And it's of course it's a commercial tool which costs like a cut. But that's what we are able to get in that point. If needed, I mean, if you think it's needed, then we could share the board or make it giving access.
Well, clearly, I think that many people would be interested in it. I think here what we present is the low-cost solution. Like, okay, we have nothing. What can we do? Okay, that's another example. It's time to conclude. So on the bright side, as a conclusion, on the bright side, I think the kernel has actually everything we need, almost, or with limited cost. If anything is missing, if we miss some power management events, we can add it very easily, like with the print K, or it's easy to add. What we miss is actually the power consumption data, and I would say that's probably really what we miss, because tools like Lisa is doing a very nice job, and I think what we need is just find the best way or different ways to format the collected data and make it useful for us to understand if we are doing good or bad on a given platform. I think we have many tools available. Actually, people don't really know it yet. Lisa is probably new. I know that has been public a year or two, maybe.
Yeah, 1 year or less.
Yeah. So I just discovered it at ELC Portland. So we need to maybe have more central website where we can know all the tools available. And what we know also is that we all expect different kind of tools or data being presented in different ways. But the solution from Lisa with Python, command line, and then you use whatever framework to plot the data or reformat the data the way you want, it's super cool. Well, next step, I'm here to collect more feedback on what I presented, and maybe let people go back to their own company and say, hey, maybe we should invest more in this power management instrumentation. And well, I need to work on more tooling and make those slideware ready. Thanks. Any questions?
Just to add on to the missing power consumption data.
Yes.
Yeah, internally there is a lot of data, but the problem is that it's very use case specific. You can give relative performance data for something like PS, but quote a number saying this is the power consumption across temperature, across activity, and it's very hard. You can't necessarily give one number out or give a data sheet. That's the biggest reason actually.
Yeah. There are challenges again, for sure.
And the other big problem is you can't always export the state of hardware all the way up into, say, FTrace. That you don't know when EMC is active.
Okay.
DMA,
you're right.
How long is it
So you're right. You know it's active, it's idle, or it's disabled. That's all.
So CPU, yeah, we have some information, but it's not always available. Not easy.
Yeah. One thing I really want to highlight is that it's low cost or cheap. I mean, it's having something when we have nothing. Don't expect a solution like this to be 0.1% accurate. Okay, it's going to be accurate to some extent, and maybe just enough to understand if we are doing a good job or not. I think understanding the dynamics of a platform, understanding why peripherals are being activated, deactivated, and for how long across a use case, having this picture is already great. If I am off in terms of absolute power consumption or energy consumption, that's fine. We have the dynamics. Something also I wanted to mention is I found yes.
No, you have spoken a lot of the dynamic behavior, but even the static would be a really good starting point. If we had a tool that was able to go through all the GPU state, to be sure that when we are idle, everything is almost in the right state.
Yes, because we know that when a chip is idle, and most of the consumption is going through the I/O, so making sure all our I/Os are configured the right way is absolutely critical. Yeah.
Any other question? From your presentation, what I gather is that you're already targeting boards where basically there is no firm, nothing providing you any data, and you just want to add, well, device tree or whatever, I mean, something to compute the energy consumption. my question is, I mean, since there are also x86 people in the room, what have you ever tried using something like a RAPL on x86? And if that, why not that can be the solution? But I think the answer is that basically depends on what target you want to run it on. If it's for servers where people can invest in, say, developing firmware to provide those numbers, I think it's fine, but I think that's not what we're talking about.
Yeah. So yeah, my apologies, because I'm coming from the embedded world where ARM processors are...
It's not apologies, just to understand what...
So I'm not very well aware of what's happening on x86. I know there are more data because, well, there are other things.
RAPL stands for running average power limits. It's a mechanism to basically control power. There are included power meters that you can read through CPU registers. The quality of those is variable. Let's just say, usually you have one per package. There are sometimes like domains within the package where you can get different power meters in RAPL exported to registers. And yeah, you can use them to. So if there is a tool called turbostat that you can run on an Intel CPU or Intel SoC and get the numbers from the RAPL power meter. But those are just cheap. I mean, the CPU or SoC, but there is more than that in a computer system, like on a board even. There's memory, there are other things that also throw power, and
so RAPL has a theory, but
yeah, in theory, but then first of all, it may or may not be present.
Yeah.
And second, even so, there still is more than just that in a system like on a board. Even there are different devices, different configurations, and really, if you want to get reliable data, you have to use an external power meter on the power source.
Yeah, and roughly is off by, depending on the machine, it's off by 10 to 50%.
Yeah, that I said, the quality of those power meters is variable. Some of them are quite good. Some of them are just useless.
So is it not based on energy model, not an actual energy counter, but there is an energy model, some kind of formula to figure out this?
There is always an energy model involved because you have to, essentially you can't measure several things at the same time and relate, so you can try to do it, but you have to relate them to each other in such a way that it's feasible. The fact that you measure them at different times and different scales, and you need a way to calculate the actual number it's going to be exploded. So that's how it works. But again, they are there. They can be used on some systems to get some even precise information about the CPU, power draw, and maybe GPU and SoC as a whole, but or a CPU package. But that is not a complete set of data, and still you have to measure the power in the wall, essentially.
Yeah, but the idea, the approach will be what Lorenzo was talking about.
Well, my point is that given that it's used for power capping, right, I think it's still more reliable than whatever data is in the CPI table.
Oh yeah. So CPI tables are completely useless as far as that goes because the numbers there are just. I mean, as I said, are either made up or not present at all. So
yeah, RAPL is better than absolutely nothing.
Yeah, definitely. Yes, it is. But the coverage is incomplete. Quality is variable, and that's it.
Does it use, do you have any idea if you use strong activity counters from one of them?
Okay. Thank you.